Mr. Ainsberg here, and we are looking at lesson 5.3, which is conditional probability and independence. We're going to start with conditional probability, look at the formula, look at how to read it and say it, and then we're going to go into this concept of independence with probability. And this concept is, a big concept, and it's a confusing concept. And the main thing, you can kind of just write this down right now, is that mutually exclusive is a phrase that we're used to. And that does not mean independence. Like I said, write this down right now on the top of your notes. It's something we're going to come back to, but it's so hard to understand and such an important key concept. So let's start easy. Let's start with conditional probability. Now, conditional probability. And so we assign probability to an event, and it can change if we know another event has already occurred. So really what these first two bullet points are saying is, we're looking at an event already happening. So there's some probability of an event already happened, and we're looking at what happens after that event. What's the probability of that second event occurring given that first event occurred? So conditional probability is saying, hey, something already happened, and the probability of the next event is affected by that first probability. And so that's conditional probability. And I'm going to read it to you too. The probability that one event happens given that, in that phrase, given that another event is already known to have happened, has already occurred, is what conditional probability is. And we use, if we have event A, we have event B, so we say the probability that event A has already happened. So we want to find the probability that event B happens given that event A occurred. We denote it with this notation. Probability B, vertical bar, A, it's read as either given that or under the condition that. So the probability of B given that A occurred, or the probability of B under the condition that A occurred. So that's conditional probability. And what we're going to do is we're going to focus first on something we are comfortable with. We're going to look at two-way tables with this. So let's start. In this example, we are looking at grade distributions, and it's from the University of New Harmony. They have 10,000 grades that they collected last semester. That's from a liberal arts school, it's from an engineering and physical sciences school, and it's from a health and human services school. We can see it in the two-way table on the screen. We have the totals as well for the rows and columns. But the most important thing, and I said this in my previous video, is it defines the variables. Remember, if you don't define it, you don't get to use it. And so notice you see I've highlighted here. It's going to define the event E as a grade coming from an engineering and physical sciences course. It's going to define event L as a grade lower than a B. And so we're being asked to find these three probabilities. And I miniaturized the table and put them underneath so I can kind of zoom in and show you what each one would be. So first is just asking for the probability of L. Remember, L represents a grade lower than a B. So this is something that is not really conditional. We're looking at just one event. Well, if I want to find the probability of just event L occurring, a grade lower than a B, I'm going to focus on this column. And let's just make this a little bit thinner. And so I'm going to focus on this column right here. Well, how many students received a grade lower than a B? Well, we're going to look at that total. I'm thinking it's going to be 3,656. Well, how many total people were there? Well, there were 10,000. So the probability of event L is 3,656 over 10,000. Now I could convert that to a decimal if I needed to, but we're going to leave that alone. Not conditional. Basic probability from the previous video. However, when we go to the second example, that's where we see a condition. We want to know the probability that the grade comes from an engineering and physical sciences course, given that the grade is lower than a B. So now we have a condition. Event L is going to occur first. And so again, event L represents this blue column. Given that a grade lower than a B already occurred, what's the probability that it came from an engineering and physical sciences course? And so that would be this row right here. So when I look at this, notice there's an intersection there. We can see that 800 students in engineering and physical science courses received a grade lower than a B. So now we know 800 is probably going to be the number in the numerator. It's the number of times that event occurred. Given that column B, row, well, engineering and physical sciences, that row happened. And so now I'm going to have this. I've got to figure out what's the total. Well, the total is going to be based off of that 3,656. The total is going to be based off of that number because that's the event that occurred first. And so our final answer is 800 over 3,656. Again, I can convert to a decimal if I want to. I'm just going to leave that alone. So we have that condition, and that condition tells us where to focus first, and then we look at what the event is next. So when I look at this one, this time they're flipped. Now I want the probability that you have a grade lower than a B, given that it came from an engineering course. So now the first event, the event that's going to set everything off, is that it is coming from an engineering and physical sciences course. That has to occur first. Then we look at a grade lower than a B, which was this column right here. And so when I look at this, where do these intersect as well? Well, these intersect at the same place. They intersect at 800. But notice, what is the first event this time? The first event this time had 1,600 total. That engineering and physical sciences college, that grade had to come from there. There was 1,600. So our answer here is 800 or 1,600 or 0.5. This is conditional probability. You're analyzing an event occurring and then another event happening after that. So that's where we get the given that. So we have right here independent events. We're going into this concept, which is a very, very tough concept for to really understand. Now, good news is mathematically pretty easy to prove independence. But understanding when reading and comprehension is something that takes a lot of practice on. And we're going to see an example of one from our previous AP exam. So this was defined in the previous version of our textbook. Two events are independent if the probability of B given A does not change the probability of event B occurring. It equals the probability of B. So easy to say, hard to understand. So let's try this again. Event A happened, and I want to know what the probability of event B is after event A. If that's the same probability of just event B occurring all by itself, then they are independent. Event A did not influence event B at all. Now here's a basic kind of, I'd say, well, basic, here's this idea with foreclosures. We can analyze what's the probability of just houses being foreclosed. Now what if we set a condition? What if instead of we say, hey, what's the probability of houses being foreclosed? What if we set a condition of a city? What is the probability of a house being foreclosed given that it's in Columbus? Is that equal to the same probability of any house being foreclosed on? And that's the idea, is sometimes some events do have an impact. Now we can kind of think of it in a way that maybe you can understand a little bit better. What's the probability that your class is going to do well on a test given that another class has already taken that test? Is that going to be independent of you just doing well on that test? So really, I guess we're saying is, did somebody in the previous class give you information? It's that idea, is the probability of you doing well on a test, given that another class has already taken it. These two events aren't independent of each other. You doing well on the test is not going to be independent of another class already taking the test, because they probably told you some information about that test when you're walking down the hallway thinking that we don't hear you. But that's independent events in a very beginner understanding. Let's go a little bit further with it. So now we look at an example. And this is where I say mathematically it's a little bit easier for us to do. Is when we have this idea of independence, we say knowledge that one event has already happened does not change the likelihood that another event will happen. We say those two events are independent. So that's where we get the idea of the probability of A, given that B occurred, equals the probability of A. That event A was not influenced. It did not change. That probability did not change because event B happened. It stayed consistent. And that's what independent means. The probability is going to stay consistent no matter what happened in that other event over here. Or we could do it's the other way, probability of B given A is going to equal probability of B. Event B is not influenced by event A occurring. The probability is consistent. It is equal. The probability of B given A is equal to just the probability of B. Again, it's a very hard concept to comprehend. And one of the things that people do confuse is mutually exclusive and independence, which is why I told you to write that down in the first slide. They do not mean the same thing. This idea of independence, if I do a Venn diagram, it does not mean this. Event A, event B. That's mutually exclusive. These are not the same ideas of it. And that's where we're going to get the tougher stuff comes into play. So here's what we're going to do. We're going to look at this example. Are the events of being male and left-handed independent of each other? And so you have to kind of take yourself away from the situation. In other words, remove your personal opinion, remove your bias from the situation. Don't go, well, being left-handed isn't influenced by being male, or being male isn't influenced by being left-handed. Remove that. Rely on the probability from it. So remove your interpretation, remove your bias from this. And we're going to prove it mathematically. We're going to prove it using the probabilities. And what we'll do first is we will look at, and I'm going to do the right-hand side, let's just find the probability of being left-handed. So the probability of being left-handed, if I kind of do the same thing with highlighting, well, here are the left-handed people. There are 7 out of a total of 50. So that tells me the probability of someone, based off this data, being left-handed should be 7 out of 50, which is 0.14. So now I have that. So I want to know, is the probability of being left-handed independent from the probability of being male? Is the probability of being left-handed, given that the person's male, equal to just the probability of being left-handed? So let's do our conditional probability now. So probability of being left-handed, given that, and so I'll erase this, given that they are male. So given that this event occurred first, that event occurred first, what's the probability of the person being left-handed? And so now we're looking here. Well, where do these two intersect? Well, you have 3 of them. Out of how many in this case? Looks like 23. So 3 out of 23. 0.13. Man, those are really close. They are 0.13. If I were to look at the decimals, and 0.14, man, I bet you they're really, really close. But close doesn't count. They have to be exactly the same no matter what. So these probabilities are not equal. So therefore, the events, male and left-handed, are not independent of each other. So that's how we're going to prove it mathematically using probabilities, is you find the probability of the one event, then find the probability of that event given that another one occurred, and that will tell you whether those 2 events are independent of each other. If they are equal, they are independent, because that means being left-handed was not influenced by the event being male. So if they're not equal, if they're close, if they're not equal, doesn't matter if they're close, they are not independent. So mutually exclusive versus independent, and this is what I had you write on the front page, is they are not the same. They do not mean the same thing. And we can prove it, of course. Being Mr. Rainsberg, I love proving things mathematically, is let's prove it mathematically. If 2 events are mutually exclusive, that means there's no overlapping. And that's where I drew the Venn diagram for us. It's boom, boom, boom. Here it is, event A. Here is event B. If they are mutually exclusive, there is no overlapping. The probability of event A and event B occurring is 0. Now, independence. We can say, we did this before, the probability of event B given that event A occurred has to be the same as just the probability of event B. That's independence. Now we can write this conditional probability, event B given A, using a formula. And this is the formula right here. The probability of event B given A is going to be equal to the probability of the overlapping, because that's what this represents. This represents the overlapping. And therefore, the overlapping of it, if they are exclusive, is 0 over the probability of just event A. Well, if they are exclusive and there's no overlapping, well, the probability of event B, given that A occurred, is 0. So independence can't mean the same thing as mutually exclusive. Because when I use the conditional probability formula, the probability of B, given that A occurred, in their mutually exclusive events, I'm going to always end up with 0 in the numerator. So therefore, mutually exclusive cannot mean independent. We can prove it mathematically, but you have to understand it up here. Is if event A occurred, so this right here occurred, I'm focused just on that purple area. What's the probability that event B is going to occur? Well, there is no event B inside of here. It's 0 on it. So mutually exclusive does not mean independence. Now, again, we proved it mathematically, but you have to understand it. So let's think of cards. Probability of hearts and spades. So I want a card that is both a heart and a spade. And the probability that that's going to occur is 0. Because there are no hearts that are spades. In other words, they are mutually exclusive. There is no overlapping on it. But if hearts and spades are independent, then the probability of a heart, given that a spade occurred, the probability of drawing a heart, given that you drew a spade, is 0. I mean, you can't do that. You can't have a heart that's a spade. We just explained that. But what's the probability of drawing a heart? Well, it's 13 out of 52. If two events are mutually exclusive, what we're going to say is they are not independent. They are not independent. And just think of it like the cards. And maybe I said it too fast, so we'll just do it one more time. Is you're drawing from a deck of cards. You want to know the probability of just drawing a heart. And that's where we get 13 out of 52. That makes sense. Now, what if we look at a condition? What if you had an event occurred? What if you drew a spade? And so you have a spade. What's the probability of drawing a heart given that you drew a spade? 0. Because there is no chance that that spade is a heart. And they're not equal to each other. So therefore, those two events are not independent. They are mutually exclusive, but they are not independent. So if two events are mutually exclusive, they are not going to be independent. And that's where we get this mathematical idea that conditional probability will always be 0 if they're mutually exclusive. Now here's an example from 2002. It was a multiple choice problem on the AP exam. It says, which of the following statements is true for two events, each with a probability greater than 0, which means they have a chance of occurring? A, the events are mutually exclusive, then they must be independent. And notice, this right here is kind of what we've been saying for the past 5 minutes, is they do not mean the same thing. And we just proved mathematically that mutually exclusive and independence are not equal to each other. But that is the biggest, the most chosen wrong answer by students, because even our brains want to say they mean the same thing. But one of them is based off of probability given that something occurred. And one of them is saying, hey, is there any overlapping over here? So it's not going to be choice A, but choice A is the most selected wrong answer for this, because people want to say those two mean the same thing. If the events are independent, they must be mutually exclusive. If the events are not mutually exclusive, they must be independent. Now, maybe you're leaning this way. Well, they're not mutually exclusive, so that means they are guaranteed to be independent. But they're not guaranteed on it. It's not 100% chance of them being independent. There's a possibility, if they're not mutually exclusive, there's a possibility that they're independent. Not guaranteed to be 100%. If the events are not independent, they must be mutually exclusive. If the events are mutually exclusive, they cannot be independent. Now, I'm going to cross out B, and I'm going to cross out C. Because B, if the events are independent, they must be mutually exclusive. No, we've discussed that already. If the events are not mutually exclusive, they must be independent. It's a possibility. It's not guaranteed. So it's not the most correct answer. So I'm looking at choices D and E here. If the events are not independent, they must be exclusive. So that's a guarantee statement there. That has to be 100% of the time. Now let's read choice E. If the events are mutually exclusive, they cannot be independent. That's the answer. That was the idea of the previous slide. We can prove it. Is if they are exclusive, there's no overlapping. So the probability of B, given that A occurred, will always be 0 in mutually exclusive events. So therefore, it won't ever be equal to just the probability of the original event. This was a very tough problem on the 2002, and I know 2002, almost 20 years ago, but this concept still is here, and this is stuff that the students still struggle with, and it's hard. Like I say, mathematically, we can do it. We can do this problem with left-handed and male. Makes sense. They have to be equal mathematically. But when it comes to definitions and concepts, that's a little bit harder. So here we go. Some other things from a different source. If two events are independent, the outcome of one will not affect the outcome of the other. So whether or not it rains and whether or not a coin flips heads or tails. If two events are mutually exclusive, if one happens, the other event cannot happen. There is no overlapping. For example, if picking one M&M from a bag, I can find the probability of drawing green or red. But if I draw a green M&M, I cannot draw a red. It's green. And so we saw that 2002 multiple choice, that two events are mutually exclusive, then they affect each other quite powerfully. Because if event A occurs, then the probability of event B, given that A occurs, is going to be 0. So mutually exclusives, they do affect each other really powerfully. They kind of negate each other. Event A occurs, and you're dealing with conditional probability. Probability of event B, given that A occurred, can't happen. Thus, we go through that they cannot be, if they're mutually exclusive, they cannot be independent. They are dependent. So you see the answer for that one is choice E. So now we are looking at the general multiplication rule. And this one goes back to tree diagrams. So we're almost done. We are on slide 8. Like I said, slide 9. Bear with me a little bit longer here. So we can take the idea of multiplying along branches in tree diagrams to lead to a general multiplication rule for us. So the probability that events A and B both occur can be found using this general multiplication rule. The probability of A and B, A intersect B, is going to be equal to the probability of A times the probability of B given A. And that's where that is the conditional probability. So main idea is kind of look at this situation. Let's say I want to find the probability of 2 heads, and I'll just highlight it for you. So that means I had to, if I tossed a coin, it had to show heads the first time. That event had to occur. Now the next event is going to be, I have to have another head. And so that would be right here. And so what I'm really doing is I'm looking at the probability of the second coin flipping to be a head, given that the first coin was a heads. And so I can multiply those two branches, the probabilities assigned to those two branches together to get 1/4 on it. It's a very basic example for us to kind of understand what's going on. Is we looked at the first event, tossing the first coin. We looked at the second event, the probability of getting a heads on the second coin, given that the first one occurred. I can just follow along the branches for it. So here's again, blue slides, not in your notes packet. We'll kind of talk through it. And so about 55% of high school students participate in school athletics at some level. And about 5% of these go on to play on a college team in the NCAA. What percent of high school students play a sport in high school and go on to play in the NCAA? So you see this tree diagram. We were told 55% play a high school sport. And so by using the complement rule, I could say that 45% don't. We were told, and this is where you have to realize this, 5% of these athletes, and so realize this. What is this statement saying? This, you're looking at the T diagram thinking, well, it makes sense, but read this statement. And about 5% of these athletes, of the 55%, 5% of those. So look right here. That's what that's telling you. The probability of athlete going to the NCAA sports, given that they played a high school sport. So notice that given that is there. So that's where we put this 0.05. Given that they were in a high school sport, they have a 5% chance of going into the NCAA. And then we can use the complement rule again, and that's going to give us our 0.95 here. Now, we were told nothing about if they don't play high school sport, what's the probability of going in the NCAA or not going in the NCAA. That we weren't told, so we're just going to leave those branches alone with question marks. So if I want to find the probability of high school and NCAA, I'm going to take the probability of high school, which is, and I'll erase the complement rule, 0.55. I'm going to take that 0.55. And I'm going to multiply by the probability that they're going in the NCAA, given that, follow along, given that they played it in a high school sport. So that's that 0.05. And so that given that, we multiply those together, I get 0.0275. So there's almost a 3% chance of high school students who play a sport in high school and in the NCAA. So almost 3% of high school students will play a sport in high school and in the NCAA. This is a very kind of introductory concept of the tree diagrams in the idea of conditional probability and the general multiplication rule. We can follow the branches. Let's do this one. 2 shipping services offer overnight delivery of parcels. This is slide 9, people, and both promise delivery before 10 a.m. A company ships 30% of its overnight packages using shipping service 1 and 70% using shipping service 2. Service 1 fails to meet the 10 a.m. promise 10% of the time, and Service 2 fails to meet the promise by 10 a.m. 8% of the time. What is the probability a package will be late? So I'm looking at this as a state plan do conclude, that 4-step process. We're going to start to see that pop up more and more and more. State, well, we're trying to figure out what percent of packages will be late. That's what the problem's asking us. It's not specifying which service, it's saying what percent of packages will be late. So we're going to plan, we're going to create a tree diagram. You can see that right there. And that tree diagram is going to show us branching off into service 1, branching off into service 2. Those are the 2 services. That's the first event that happens. Now, then what happens is, well, they're either going to deliver the package on time, not late, or they're going to deliver it late. And that's for both services. You can see where those branches come off. We want to find the probability that you have a late package for both service 1 and service 2. So let's take a minute and fill in this tree diagram. So when we're looking through this, the first thing it tells me is that a company ships 30% of its overnight packages using shipping service 1. So I'm thinking right here is going to be 0.3. So there's our 0.30. Now, technically, if we're told this company only uses 2 services, we could use the complement rule to see that the other one's going to be 0.70. But it also tells us in the prompt that 70% of the shipments are using shipping service 2. Now, if service 1 fails to meet the 10 a.m. promise 10% of the time, that means that they are late 10% of the time. Well, then how often are they not late? Well, they're not late 90% of the time then, using the complement rule. And service 2 fails to meet it 8% of the time. Well, that means that service 2 is late 8% of the time. Then how often are they not late? Well, that's 0.92. What's the probability a package will be late? So if I'm looking at this, I have to kind of pair these together for it. I have to figure out what are we trying to figure out? Late package for both service 1 and service 2. Well, here's service 1. 30% chance, well, 30% of the packages are delivered using service 1. And of those 30%, of that 30%, 10% are going to be late. So if I think of it like this scenario, I'm going to have, and I'll do green for this one, I want to find the probability that you're going to have a late package given that you used service 1. Well, in that case, using service 1 is 0.30. Of that, there is 10% that are going to be late. So when I multiply those together, I get 0.03. But we didn't care if it's just service 1. We also want to know about service 2. So service 2, 70% of their packages go to service 2. Of those packages, 8% are late. So what does this mean? We're looking at the probability of late given that they are using service 2. So in that case, I have 0.70 times 0.08 in that case. 0.056. So what am I going to do? What's the probability that a late package for both service 1 and service 2? We're going to add them together because those are two events that we're looking at here. Is the probability of using service 1 is 0.03. I'm going to add the probability of being late using service 2 to it, and so I get 0.086. So these tree diagrams are really useful with this, and the complement rule plays a role in it, and we learned that conditional probability plays a role in it as well, is that we can use it to help us with following the paths. This right here, this 0.10, is looking at, hey, what's the probability of service 1 having a late delivery? Well, it's 10%. But what's the probability of being late given that you use service 1? So the paths of the tree diagrams help us with multiplication, create a general multiplication rule for conditional probability on it. Those are slides 1 through 9. Mr. McNichols will be doing the second half of this video. Hope you enjoyed.